We are given two identical circles tangent to each other and to a horizontal line. A square is positioned with its base on the line and its top corners on the circles. The objective is to determine the area of this square. To solve this problem rigorously, we will translate the geometry into an algebraic system. The symmetry of the configuration presents a strategic opportunity. We will place the origin on the horizontal line precisely at the point of tangency between the circles. This choice is optimal, as it will induce symmetry in our coordinate assignments and significantly simplify the resulting algebraic formulation. The problem specifies that each circle has a radius of 5. Because the circles are tangent to the x-axis, their centers must lie 5 units above it. Our chosen y-axis passes through the point of tangency between the two circles. By symmetry, this places their centers at a horizontal distance of 5 units from this axis. This defines the coordinates of the centers. The left center is at -5, 5, and the right center is at 5, 5. Let the side length of the square be denoted by s. Now, we must justify the square's position. For both top vertices to remain on their respective circles, any horizontal shift would break the constraint. Therefore, the square must be centered on the y-axis. This logical necessity allows us to define its top right vertex at coordinates s/2, s. This vertex lies on the circumference of the right circle. This critical constraint forms the basis of our equation. Consequently, the distance from this vertex to the circle's center must be equal to the radius, which is 5. The standard equation for a circle is the quantity x minus h squared plus the quantity y minus k squared equals the square of r. For the right circle, with its center at 5, 5 and a radius of 5, the equation is the quantity x minus 5 squared plus the quantity y minus 5 squared equals the square of 5. As established, the coordinates of the top right vertex P are s/2, s. Substituting these coordinates for x and y into the circle's equation yields the quantity s/2 minus 5 squared plus the quantity s minus 5 squared equals 25. Expanding the squared terms results in the square of s/4 minus 5s plus 25 plus the square of s minus 10s plus 25, which equals 25. Combining like terms simplifies the expression to 5 times the square of s/4 minus 15s plus 50 equals 25. Subtracting 25 from both sides, we get 5 times the square of s/4 minus 15s plus 25 equals 0. To clear the fraction, we multiply the entire equation by 4, resulting in 5 times the square of s minus 60s plus 100 equals 0. Dividing the equation by 5 simplifies it to the quadratic. The square of s minus 12s plus 20 equals 0. This quadratic factors neatly into the quantity s minus 10 times the quantity s minus 2 equals 0. The equation yields two potential solutions for the side length, s equals 10 or s equals 2. A non-rigorous approach might simply discard one answer. We will analyze both. Consider the case where s equals 10. The top right vertex would have coordinates 5, 10. Let's analyze this geometrically. For the right circle, centered at 5, 5 with a radius of 5, the point 5, 10 lies at the very apex of the circle. This root corresponds to a different valid configuration, a larger square touching the tops of the circles, but it is not the one described in the problem. Therefore, s equals 10 is an extraneous root for our specific problem. The second solution, s equals 2, corresponds to the smaller square positioned between the circles, consistent with the problem's geometric constraints. Therefore, the unique correct side length of the square is 2 units. The area of a square is the square of its side length, s. With s equal to 2, the area is 2 squared, which results in 4 square units. This complete solution demonstrates the power of a rigorous method, establishing a coordinate system, justifying all assumptions, and correctly interpreting the algebraic results within the geometric context.